Max, how do you think we're going to tackle this competition?
Well, do you want to just knock the ball down and push it around and get a point for each lap?
Well, we could do that, but if we did that, then we wouldn't be getting very many points. To get more points, we could grab the ball off the bridge and then put it back over the bridge.
Yeah, but that's really hard. Why don't we try just to push it around and release it every time we get to the black line?
Maybe, but then it would be also hard to try to find the ball after we release it.
That's right. And we couldn't use an ultrasonic sensor or a touch sensor to turn.
Wait, I have a good idea. Why don't we get an arm that throws the ball into another catcher right over top of the bridge?
That would work, I guess. It'd be hard to build though.
Let's go try.
Okay.
So here's my idea.
Wow, I've never seen that part before.
Universal.
Never even heard of it.
So this is the ball catcher. So we'll be coming up to the bridge just like this. Toss it over the bridge, release, and let the ball go into the catcher, and then come back and go around again.
Cool. And how does it work though? How can you get it to go up like that and then close?
Well, it all works with one motor, and it's with beveled gears. And once the beveled gears can't turn anymore to make the arm close, they pull up and making it go up like that.
So how do you do that? You have like two axles in here?
Yeah, this gear is actually locked, so the rotational sensor can tell where it is at any time, and this one is attached to the motor.
Why are we using the old rotation sensor though?
Well, the other rotational sensor is in the motor, and we don't want to know how far the motor has gone. We want to know how far the arm has gone up or down.
True, because if you started using the motor when it was like this, and you were using the motor rotational sensor, it would go to there and you'd read that before you started going up.
Yes.
That makes sense. Cool arm. You have it?
We don't ever have the ball back there.
Yeah, no. We
Okay.
go draw.
Pick up
catches it.
Yeah.
Drive forward.
Let's go.
Down. And then we have to go out like that, right?
Yeah, and then no. Then it closes, picks it up. It doesn't pick up the ball. Okay, look at it. Look at this way. The bridge is right here. Yeah. When we let go, the bridge, we let it go here.
Yeah.
Then we close from up here, and then it goes backwards like that.
Yes,
and then
but
we go
then
to
we
the
come
bridge.
over again. We have to.
We pick up the ball before we go to the bridge, pick it up a bit, drive over the bridge. The bridge is now here. We drop the ball.
Okay, so yeah.
Yeah.
So you're never doing it where we have to like pick up and then go down and drop it.
Yeah, we never do that.
You just have to go pick up the ball. Wait, so pick up the ball.
So the question that I asked was why would you use these two big wheels and two small wheels? Also, why didn't you use why exactly slide? Why not like little wheels like these exactly? Not exactly this big, but these.
Well, because these are just so much smaller that they'll be able to.
They're thinner.
Yeah, they're thinner.
It reduces our robot silhouette essentially.
And
Makes
it's
it easier to slip
small.
by.
Yeah, and also these, if you see, they have the rubber on it. If they didn't have the rubber on it, this would be fine. We could put these here, but we didn't want to because those are just smaller. If we had the rubber on it and we tried to turn with 4 wheels, it would just go like this. This wouldn't even move. It wouldn't turn. Because the rubber would catch and
You
it would
need
just...
to have it so both the wheels are geared together if you want to do that.
Yeah.
That's why tracks work better if you're going to have 2 wheels that aren't running. Because the other wheel is driving.
Exactly.
And you can make a ping pong ball shooter with the.
Okay, say it again.
Why are the motors facing upwards and not flat down?
Well, for this to fit onto the base, we needed the motors to be out of the way. And for the motors to be out of the way, we could have them go up or to the side. So we picked up. And also when the arm goes up and down, when the arm goes back down, it kind of jerks it because it has so much weight that this is where the arm goes down. So there's now more weight on this side so that when the arm goes down, it won't jerk it like it does on the prototype.
Hey Michael, so first question, why did you use 2 rubber tiles and 2 of these little tires?
Well, mainly
Not tires, sorry.
sliders.
Sliders.
Well, these are the drive wheels, so they need to have the rubber so that it can pull, so it has more traction. And also the back wheels, if they had rubber on it instead of just plastic, they wouldn't slide.
Yeah.
They would grip and wouldn't turn.
And we don't want that because then it would make turning a really big ordeal. You have to do tank turns.
Why did you use sliders and not 2 more rubber wheels?
He just explained that.
Because the turning.
Oh, okay.
Yeah, because otherwise you have to do tank turns, and that's slower than if we
What's
could
tank
just get it.
turns?
Okay, so a tank turn is one goes forwards and the other goes backwards, so you get it to turn on the spot. And we want it to do, what we want it to do is go like around, and that way it's smooth, not short, jerky, turning like this. So a tank turn would be like this.
Yeah. What if the height of the bridge is lower
Max, we'll show
than
them.
the, yeah. What if the height of the bridge is lower than this?
What we make.
Okay, yeah, what would we,
Well, we could, because of the way Michael built this with these pegs here, you can take these out and raise it up and down along these pegs. And same with over here and over here. You just move them up and down. And it makes it much easier to lower because we just drop it down. And same here.
And same for the ball catcher, it can go up and down,
The ball catcher.
just in case the bridge is higher or lower.
Why does your claw have angle on it?
So it can get over the bridge.
straight, then
If
it'd
our,
be like
if our
this.
claw was straight, it'd go like that. But since our claw is forwards, we just drive under and go.
See if the claw was straight, it'd be up like
Yeah, we'd hit it, and it would be up, and we wouldn't be able to pick up the ball. We do the same thing as it does when you try to pick it up off the ball catcher. When you put it down on the ball catcher, you're reeling it up.
Go ahead.
Hey Max, I was just looking at this robot and I realized you had an ultrasonic sensor. Why?
Well, before our robot would not know where a wall is, and so it'd be going, it would bump into this wall, then bump into here and screw it up. But now with the ultrasonic sensor, it will drive until it's a certain number of centimeters away from the wall, in our case 17, before turning. So that way it doesn't bump into the walls anymore.
Is there any other issues you had with this robot?
Well, we had tire slippage because we were going from 0 to 100, which caused the tires to spin. And then when we went from 100 to 0, they'd skid. So to eliminate that problem, we've introduced a program called Ramp Up, Ramp Down. And what that means is it starts at 20 speed and then goes until it reaches 100 speed. And then it drives for a while, and then it starts to deaccelerate until it's back at 20 speed and turns. And that eliminates our tire slippage.
Is there anything you're planning on doing with this robot to make it better?
Well, right now we have an avoidance program that we're building, and what we do is we set a minimum distance, and if anything is lower than the minimum distance, our robot just stops and waits for it to become greater than the minimum distance.
All right, thanks for answering my questions, Max.
You're welcome, Hussein.
You're too tall.
2 days before the competition, our ultrasonic sensor is giving us faulty readings. We can't do our avoidance program because of it. So, in other words, we're screwed.
So we've decided to just build the program without the ultrasonics, so we're not doing any avoidance, and we're just going to run blind for the 3 minutes.
And what we're hoping is if we get stuck, which we hope we don't, we can just press one of our buttons. It's called the state machine. It will reset our program back to the beginning without resetting our timer, and we can continue until our timer runs out.
Yes.
And how we have that working is when you press the button, it says, has the button been pressed? If yes, it goes back to the first step and waits for us to start it up again. Thank you for watching our video presentation about the challenges we faced and how we overcame them at the 2010 Halton Skills competition.
Thanks.